Today we'll be going over gases and their properties as well as the gas laws. This will cover Texas Competency 13 and Team 10.9a. The kinetic theory of gases describes a gas as a large number of atoms or molecules in constant or random motion in a non-defined space or volume. As you can see from the image above, all the molecules are moving around in no particular path and are colliding with the edges of the shape. The physical properties of gases are pressure, temperature, and volume. Essentially, this theory proposes that pressure is due to collisions between molecules moving at different velocities. So not only are these colliding with the walls of the container, but are colliding within themselves. There are several variables that affect gas behavior. One being volume, which is always measured in liters. It should always be converted back to liters if measured in milliliters. 2 is pressure, which is measured in atmospheres or millimeters of mercury. 3 is temperature and is measured in degrees Kelvin. If a problem gives you the temperature in Celsius, you would just use the conversion below, which would be 273 plus whatever temperature of degrees Kelvin you are given. And just as a note, at absolute zero, no heat is present in the system. And the quantity of gas is always measured in moles. So what makes a gas different from solids and liquids? Gases have a higher kinetic energy content, which means that their motion is much greater than that of solids and liquids. Gases have lower densities, they have fluidity, they flow and take shape of their container, just like liquids would do. And when it comes to solubility, they respond to changes in temperature and pressure. How do gases respond to temperature? As the temperature of a gas increases, its volume increases. This is due to the fact that heat makes gas molecules move faster and they need more room to do so. So the collisions are increasing, and this is what's causing the expansion. So in the picture here, you can see at 0 degrees Celsius, our balloon is relatively small. And over here to this side, we have the second balloon, at the same balloon but at 20 degrees Celsius, which has expanded to a much greater size due to the increase of temperature. This relationship is called Charles' law. As the temperature of a gas increases, the volume increases. This is a direct relationship. So from this expression, we can see that volume 1 over temperature 1 is proportionate to volume 2 over temperature 2. Let's work out a little practice. So we have a sample of gas that occupies 3.5 liters at 300 Kelvin. What volume will it occupy at 200 Kelvin? Here I am underlining our key points. So we have a gas that occupies 3.5 liters. This right here would be our initial volume. And it's occupying it at 300 Kelvin, which would be our temperature, our initial temperature. What volume we're looking for? Our final volume will it occupy at 200 Kelvin, which is our final temperature. So using the expression on the page before, we can plug in, using Charles' law, we can plug in the numbers of the known values. So we do know we have 3.5 over 300 equals, we do not know what our volume 2 is, over our 200 Kelvin. This being said, we would just solve for our volume 2. So rearranging everything, cross-multiplying, and then dividing by 300, volume 2 would give us 1.26 liters. And remember our significant figures, and we keep 3. We would keep 2 only, because this one. So 1.2 liters. So that's how gases respond to temperature, but how do they respond to pressure? As the pressure on a gas increases, its volume decreases. So by adding pressure on a gas, you're decreasing its space. From here in this image, you can see that the volume here is much greater. But as we apply pressure from the top, we are decreasing the volume, which is increasing the pressure and causing much more greater collisions among the gases. This is an inverse relationship. As you can see from the graph as well, as the volume is greater, our pressure is much smaller. But as we decrease the volume, our pressure becomes much greater. So larger pressure, small volume. This is Boyle's law. As pressure goes up, volume goes down, and this is an inverse relationship. It would be pressure 1 times volume 1 equals pressure 2 times volume 2. So let's work an example. It is hard to begin inflating a balloon. A pressure of 800 kilopascals is required to initially inflate the balloon to 0.225 liters. What is the final pressure when the balloon has reached its capacity of 1.2 liters? So we know that we have 800 kilopascals, so this would be our pressure 1. We know that our initial volume is 0.225 liters. What is the final pressure when the balloon has reached its capacity of 1.2 liters? 1.2 liters would be our final volume, and we are looking for our final pressure. So we would just substitute this into Boyle's law, which is V1 times P1 equals V2 times T2. So V1, 0.225 times P1 times our 800 kilopascals equals 1.2 times our P2. So we would multiply these across and divide by 1.2, and this expression would give us P2. Once you do all the math, you should come out with P2 equaling 150 kilopascals. Another expression law to keep in mind is Gay-Lussac's law, and this states as the temperature on a confined gas goes up, its pressure increases. So this is also a direct relationship, just like Charles' law. Pressure 1 over temperature 1 equals pressure 2 over temperature 2. And this will give the same relationship as Charles. We also have a combined gas law, which is combined law of Boyle's, Charles, and Gay-Lussac's law all together, and it allows us to calculate the effects of temperature, pressure, and volume on a gas at the same time. The king of gas laws, which is our ideal gas law, is pressure times volume equals moles times a constant times temperature. This, for short, it could be pronounced as Puvner, or PV equals nRT. And the variables in this equation are pressure, which are in atmospheres, volume, which is in liters, moles, temperature in Kelvin, and R is our gas constant. This value will never change, and it is measured at 0.0826 atmospheres times liters divided by moles times Kelvin. The ideal gas law applies to gases in ideal situations and not to real-world gases. So let's go ahead and work out a problem using the ideal gas law. So we want to know how many moles of xenon are in 2 liters at 0 degrees Celsius and 2 atmospheres. So we want to know moles. So we do not know moles. We know we have 2 liters as our volume. Our temperature equals 0 degrees Celsius. and our pressure equals 2 atm. And we already know that our gas constant does not change. So that is just 0.0826. So really quickly here, our temperature is in Celsius. To change this, we need to add 273. Since it's just 0 degrees Celsius, our temperature now would just be 273 Kelvin. So let's go ahead and plug this all in into our PV equals nRT. So our pressure is 2 atmospheres. Our volume is 2 liters. We do not know our moles. We have our gas constant, which we know as 0.026, and our new temperature, 273. So we go ahead and do our math and use our algebra. We have our 4 over here equals our n, and then we go ahead and multiply our 0.0826 times 273. That'll give you 22.54. Just simple algebra, but I'm going through all the steps with you. And then go ahead and divide out by 4 so that we do find out how many moles we have. So that gives us 5.64 moles of xenon. And that is how you would solve an ideal gas law problem. Just make sure to know what variables they're asking for, what variables you are given, and make sure to check all your units to make sure that they are converted into the right ones.